Hello dear participants, I welcome you all again here in this certificate course. We are starting module number 2 today, and the title of module 2 is Inferential Statistics using MS Excel and S.P.S.S. So we all are here in the lecture number 25 of this course with the title Introduction to Inferential Statistics. Objective of this lecture number 25 is to make you all familiar with the inferential statistics. As we all know that we classify statistical techniques into four different parts. First is descriptive, second is inferential, third is associative, and fourth is predictive. In most of the books, associative and predictive been considered as a part of inferential statistics. In the descriptive statistics, there are different three methods involved in. The first is tabulation method, second is graphical method, and third is numerical method. In the previous module number 1, we tried to understand that how can we construct different types of tables and different types of charts for different types of variable like nominal, ordinal and scale variable. Moreover, we also tried to understand that how can we give numerical treatment on the different variables like scale, ordinal and nominal, where we understood that if we are having the scale variable, then we can give plenty of numerical treatments on it. But if we are having the nominal and ordinal variables, then there are some limitations to give plenty of numerical treatments. So all this part we already have seen in the module number 1. If I go graphically, then if a distribution is given to you, then initially we tried to find out the central value, where we tried to compute arithmetic mean, median and mode. All these three concepts are having their own meaning, and we already have seen that how to compute all these things and how to read and interpret the values associated with central tendencies. Then we shifted to the dispersion, where we tried to understand that how to compute range using max and min. Then we tried to understand that how can we divide our distribution equally into four parts using first quartile, second quartile and third quartile. And then we tried to understand that what is interquartile range, what is quartile deviation. And in the dispersion, finally we tried to understand that what is standard deviation. Standard deviation is the average distance of the values from the mean, and that standard deviation also denoted by this sigma. Then we have seen that how to draw a histogram with a normal curve. So this blue line is nothing but a normal curve, and normal curve actually plays a very important role in the inferential statistics. We are going more deep into this, but little later. Let me first revise the things which we already have seen in the previous module. So in the previous 2-3 lectures, where we try to understand the skewness and kurtosis, there we have seen that for almost all our variables are having almost fairly symmetrical distribution. What does that mean? What is fairly symmetrical distribution? It only tells me that my skewness value is less in numerical way, but in a graphical way, when I am saying that my variable is fairly symmetrical, it tells me that this distribution is in a such a way that 50% distribution is on the right side of the central value and 50% distribution is on the left side of the this central value, and this curve is a normal curve. This curve is a normal curve where your mean is almost equal to median and mode. For height of the respondent also, again it is fairly symmetrical because this value is means minimum value. So approximately the 50% distribution is on the right side and 50% distribution on the left side. Why I am explaining all these things so intensely here? Because this normal curve plays a very important role in the inferential statistics. Fine. What is the meaning of all these things that we are going to see in the few upcoming slides? Again, here in the weight also, here it is fairly symmetrical. There are only few cases, like here in the income of the respondent, it is moderately skewed. But if I increase my sample size, now if you remember, here the sample size is 100, n is equal to 100. If I increase this, and if now the number of observations are 1000, then this curve tends to be fairly symmetrical. It tends to be fairly symmetrical, where you will find that the 50% distribution is on the right side and 50% distribution is on the left side. However, in the previous module we have seen all this part. So what are the functions, or what are the important features of the descriptive statistics? The first feature, typically if you are having the data with us, typically first we should go for the descriptive statistics, because it is used early in the analysis process. Fine. If we are having the data with us, then first we should go for the tables, simple tables. Then we should go for the graphs, different graphs or charts, and then we should go for the numerical treatments here in the descriptive statistics. Why we should follow this? Why should we follow all these steps? Because it helps us to understand the nature of the data, and it also reveals the general pattern of the responses or my data. Fine. It also helps us to reduce the data. And finally, and a very important function or the feature here is it is a foundation for the subsequent analysis. So what type of the subsequent analysis that that actually means, for which the descriptive statistics is the foundation? That subsequent analysis is nothing but it is inferential statistics. So let me take you all to the meaning of inferential statistics. What is inferential statistics? Inferential statistics are used to generate conclusions about population's characteristic based on a sample data. So inferential statistics actually works on sample data, but it actually works for the population characteristic. It works on the sample data, but it actually works for the population characteristic. What are the functions or the features of inferential statistics? First function, typically it is used after descriptive statistics. Again, if I am having data with me, don't go directly for the inferential statistics. First, go for the descriptive statistics and use the different methods involved there in the descriptive statistics. Then we can go for the inferential statistics. Fine. It works with the sample data. It helps us to make inference for population, and it helps us to draw conclusion about the population. So that was all about the features of the inferential statistics. Now what actually we do in the inferential statistics? Let's understand this thing. In the inferential statistics, here we assume that we have computed the descriptive statistics, and now we know the nature of our data. Now what first step that we take here in the inferential statistics? Here the first step is we make a certain claim or a hypothesis about a population characteristic. When we are making certain claim about population, that is known as a hypothesis. It means I am saying that say that the mu is something, any particular number. You are making one statement for your population. Fine. Then what we do? We collect the samples, and for sampling we use the probability sampling. Why probability sampling? Because from this population, if I select my samples randomly, then these samples now they becomes the means proper representatives of the that population, and they gives me the values, which values, using which values I'll compute some particular sample statistic, and that value, using that value I can estimate for the population, because here I have used the scientific method. I've used the random sampling, probability sampling. Fine. Now here the sample information is invariably more accurate than the hypothetical value. When I'm saying this, means when I'm making this claim is a hypothetical claim. There are no proofs. Fine. But to check whether whatever I am saying is correct or wrong, for that what I do, I identifies the sample, I collects the data, and I compute some value, and then I compare this value with this mu. It means I compare what? I compare the population mean or the hypothesis or that particular population characteristic with the actually computed mean from the actual data, actually collected data. Now when I compare this thing, then here I try to see that whether they are equal or they are not equal. And to come to the conclusion, we use test statistic. So what is test statistic? In simple terms, in the descriptive statistics, there are different measures of central tendencies, correct? So there is mean, there is median and more. So all the three are showing me the same thing, that the center of the data. Now here in the inferential statistics, I am going to compute, or I am going to compare two things, that is say that population characteristic or a hypothesis or a claim, some claim, and the sample statistics, and I'm going to check whether they are equal or they are not equal. But how to test this? To test this, we are going to use different test statistics, different methods, like there are Z table is there, T tests are there, F tests are there, or the chi-square. There are different tests like mean, median, mode here in the central tendency. So test statistics are nothing but they are the different techniques using which we try to compare, or we try to check the difference between sample mean and hypothesized mean. So this is the way that inferential statistics work. Now let me take you to the some images or pictures, like here is a population, and in this population there are plenty of samples, there are plenty of samples. Now as a researcher, what I'll do, I'll follow one technique like probability sampling, and then I'll identify my samples. So once I identify these samples, I collect the information, and I compute something, say that mean. This arithmetic mean on the basis of this sample data is known as a sample statistics, and on the basis of this I make the inference, or I estimate the population parameter. So this is the thing that we do here in the inferential statistics. Now before going to the hypothesis testing or the more technical part, let me discuss here few basic terminologies which we are going to use during this module. So the first terminology is normal distribution. What is normal distribution? In very brief, in the previous slides we already have discussed that for most of our variables we have drawn this kind of curve where the skewness is 0. If the skewness is 0, then that curve is known as a normal distribution. And what is this normal distribution curve? Here your mean is equal to median is equal to mode. If my skewness is 0, then this criteria get fulfilled. Now here the 50% distribution is on the right side and 50% distribution is on the left side. Here is the central value, here is the population mean, and this whole distribution is computed using only two things, that is mu and standard deviation. This sigma is nothing but this is a symbol that we use for the standard deviation. So here we are going to use only 3 standard deviations on the right side, plus 1 standard deviation, plus 2 and plus 3, and on the left the same 3 but with the minus sign, minus 1 standard deviation, minus 2 standard deviation and minus 3 standard deviation. What does this mean? It means I'm having plenty of responses here. There are few responses who are more than this mean, and there are many responses who are less than this mu. Here is the central tendency, and this dispersion or this distance that we are going to compute within the 3 standard deviation, plus and minus. Fine. So normal distribution provides the basis for statistical inference. The most important thing, all this is logical, all this is theoretical. So this distribution is a theoretical. We never go for the population study. We never collect the all information of all our population. Fine. We only go for the sample. We collect the responses, and on the basis of that we compute something using which we estimate for this mu. But there is one concept, that is normal distribution, and in the upcoming slide we are going to see that what is Z distribution. So that distribution only tells me that if I collect all my information for the population, then this distribution looks like this for the population. Fine. Many variables have distribution that closely resembles the theoretical properties of normal distribution. We already have seen that that the normal curve for the age and the height and the weight, there we have seen that they all are fairly symmetrical, but they are on the basis of the sample. Now if I compute population, then they will appear exactly symmetrical, normal distribution way. Fine. Now the area under curve, this is also a very important concept. Total area under this curve, normal distribution curve, is 100, where the 50% distribution is on the right side and 50% distribution is on the left side. Fine. So the area under the normal curve are tabulated and shown in Z table. In the statistics there is particular Z table available in every book, where it only tells me that if there are 2 points, then how much portion of the normal distribution curve those 2 points covers, where those 2 points are located. So all this is a technical part. So far this course is concerned, we just want to make you familiar with these terminologies. When we go for the software, the process part is simple and the interpretation part is also very simple in the hypothesis testing. But before going to the hypothesis testing, we need to know what actually the normal distribution is. So now, as I said, that the whole area under this curve is the 100%, that's fine. But the area between these two standard deviations, that is plus 1 standard deviation and minus 1 standard deviation, the gap between these two dispersion values is, it covers the 34.13% of the total area. Out of this 100%, if I add both the numbers, 68.26% responses are between 1 plus 1 standard deviation and minus 1 standard deviation. That's the meaning. Out of 100% area under this curve, 68.26% area covered by these values, or this gap between plus 1 standard deviation and minus 1 standard deviation. Now what about the plus 2 plus and minus 2 standard deviation? Now here the area covered by this portion of this normal distribution is 95.44%, and here is the minus 2 standard deviation and here is the plus 2 standard deviation. What about the plus and minus 3 standard deviation? It covers 99.72% of the portion of this normal curve, and the remaining is after this. What does that mean? It means if I collect the information on, say, that height, then what are the chances that the extreme heights like 7 feet, 8 feet, 9 feet? No, there are very less chances, but still in the whole world I'll find at least 1 or 2 persons who are having the height of 10 feet. I can find the height like 3 or 4 feet between the age group of, say, that 28 to 35. Fine. There are rare cases, and that is why this frequency is very less. Here the height is here. What does that mean? Here the average height, whatever would be the average height, I'll find that the maximum concentration of my responses is here. As I move towards the center, this curve looks like this. So all this is theoretical. Here I just wanted to highlight you that what actually the standard deviation that normal distribution is. And normal distribution is having 3 parts, that is this plus and minus 1 standard deviation, plus and minus 2 standard deviation, and plus and minus 3 standard deviation. And it only tells me that how much percent of the area under this curve it covers. So it was all about the normal distribution thing. Now suppose I'm having mean 50 and standard deviation is 10, then the distribution will be like this. As I mentioned that here is the mu and here are the different standard deviations. Then if my mean is 50 and standard deviation is 10, then 50 plus 10 it becomes 60. So my this whatever is the variable, the value 60 is actually located here. So all the responses between these two standard deviation, they covers 68.26% of the responses. Fine. Now if I add two standard deviations like 50 plus 10 plus 10, then it becomes 70. And the responses between these two standard deviations would be 95% of the responses. They should lie here in these two standard deviations. Fine. And the story is same with this. Now, if I take you all to the example which we all are familiar with this, that we computed mean and standard deviation for the age variable in the previous module number 1. Here, if my mean is almost kind of 37 is the mean, fine. And how much is the standard deviation? 12.19. So I'll consider it only 12. Now, what about this value here? What would be the value here for this plus 1 standard deviation? It would be 37 plus 12 is equal to 49. So 49 is the age here, and if I go to the opposite side, 37 minus 12, because here it is minus 1 standard deviation, it comes 25. So approximately 68.26% of the responses they lies between these two standard deviations. Same story with the two standard deviation here. To get the two standard deviation value, what I'll do, 37 plus 12 plus 12, I'll get 61. Here 37 minus 12 minus 12, I'll get 30. So here I'll get the 95.44% of the distribution. So this is the way that we actually interpret the normal distribution. There is one mechanism to convert the given distribution in the Z distribution. So this is theoretical thing. There is one mu and there are three different standard deviations on the right side and three different standard deviations on the left side. So this is all theoretical. But if I am having different values of x, then how to convert them into this distribution? If I just want to convert this into the Z distribution or the normal distribution, how to convert this? For this I am having the formula, but for that I need to know the mu. Population mean should be known, and standard deviation for that population, that also should be known. What does that mean? For that, let me take one example. Suppose here mu is given 100. We know the population mean, here it is 100, and standard deviation is 50. If it is 50, it becomes 150, it becomes 200, it becomes 250. Fine, so on and so forth. Now, what would be the Z value for x is equal to 200? If x is given, then what would be the Z value? Means where it is located, at how far it is located, how far this x is located from this mu. To compute this, what I do, I'll use this formula, and in the formula x is given 200, mu is there, standard deviation is 50, z is equal to 2, and if we remember, here is plus 1 standard deviation, here is plus 2 standard deviation. And what it means? It means x is equal to 200 is a 2 standard deviation above the mean. Above to this, it is located here at the 2 standard deviation, and here is the value. And this is the way that we convert x value into the z value. Fine. Now let me take you to the very new concept. What is sampling distribution? Sampling distribution means, see, our actual sample, whatever sample we choose, it is amongst the many other theoretical sample comprising the assumed bell-shaped curve of possible sample results. So the bell-shaped curve is actually a theoretical curve. It is assumed curve. It only tells me that if I collect the information of all my population responses, then the curve will look like this: normal distribution curve, bell-shaped curve. Fine. Now, what is sampling distribution? Sampling distribution only tells me that in a population there are different samples. Likewise, here, if this curve is associated with the population, and if I am choosing a particular, say that sample x, and that sample is, say that here, and from this I have computed some sample statistics x bar, then how far is this x bar from this mu? how much is the distance, because there are different samples. If someone else comes into the research area and he chooses this sample, his mean will be somewhat different. His mean will be somewhat, there are different means. There are different sample statistic. So sampling distribution is the distributions of the sample, and here we are having the standard deviation of all these sample statistics, and that is known as a standard error. So standard error, standard deviation, they are the two sides of the same coin. Only the standard error is associated with the population, and standard deviation is actually associated with the mean. Here I just wanted to highlight here that from a population, if we are working on a population, we identify a particular sample, but there are different samples in this population. Whatever mean you compute, how accurately that mean represents the population, first part. Whether is there any significant difference between the mu and this arithmetic mean is the second part. And here in the inferential statistics, we try to we try to test this difference, whether is there any difference between this mu and x bar. Now let me take you to the hypothesis related few terminologies that we'll discuss in the very brief way. So here is the normal curve. As of now you must have understood that for any variable, as the sample size increases, theoretically your curve will look like this, where your distribution would be like this, and there are three standard deviations on the right and three standard deviations on the left. All your responses are recorded here in between all these things. Now let me take it in a different way. Suppose here is the population data, and this is a theoretical distribution available with us. Now where does exactly my sample data or my sample mean actually located? Let's see few terminologies here. The first terminology is point estimate. What is point estimate? So this is a Z unit. So this is a theoretical normal distribution thing. So all those values are already computed here in the Z table. There is one specific table available in every statistics book. Now what we do, we identify the sample and we compute something, and that is known as a point estimate. So point estimate, it is a sample statistic estimating the population parameter of the interest. That's it. That's the meaning of point estimate. Now let me take you to the critical value. What is critical value? This is very interesting. Critical value, it is a table value based on sampling distribution of the point estimate and the desired confidence level. So confidence level is also one of the important terminology. What does that mean? Let me explain. If you remember in the previous slides, we have seen that there is mu, there is one standard deviation, 2 and 3. And we have seen that how much area been covered here between -2 and +2, that is 95.44% of the area. Now if I come little here, like if I come to -1.96 and if I come to the standard deviation plus 1.96 from the table, that table is there and it table tells me that much percent of the area is covered between these two values. Fine. Now if I come here, then I get exactly 95% of the area, means it is covered between these two lines, and the remaining 0.05 on the left side and 0.025 on the right side. So 0.025 on the left, 0.025 on the right. If I add both the numbers, 0.025 plus 0.025, it becomes 0.05. Fine. So what does that mean? It means 95% of the area is covered between these two extreme critical values. Fine. The remaining part, it covers the 5% of my this area. Now what is the meaning of critical value? Critical value, when I compute point estimate, on the basis of this point estimate and considering the level of confidence 95%, we compute the critical values from the table. and for the Z this critical value is minus 1.96 and plus 1.96. It plays very important role in the hypothesis testing. So please just try to recall all these things whenever they are necessary in the further inferential statistics. Now what is confidence interval? Before going to the confidence interval, see these critical values, they actually divide the whole distribution into two parts. The first part is non-rejection area. So if your mean it lies here, then we say that there is no significant difference between these two. They are same. But if my x bar lies here in the rejection region, and how we determine the rejection region? We determine it on the basis of critical value. How we decided the critical value? It is on the point estimate. So they all are linked. Here, to make it simple, if our mean it lies here in the rejection area, then we say that there is a significant difference between the population mu and mean. So theoretically we go like this. Now what is confidence interval? Confidence interval is nothing but it is a range within which population parameter fall. So lower confidence interval is here and upper confidence interval is here. This interval only tells me that I am 95% confident that my actual population mean, that is mu, it lies between these two numbers. Now what is confidence level? Confidence level, it is the probability that the population parameter fall in confidence interval. So 95% is the confident. I am confident that I am saying that my population mean lies between these two confidence interval. And what is level of significance? Level of significance is the probability of rejecting null hypothesis when it is true. So this is kind of technical. Just try to understand that there is 1.96 here on the right side, there is minus 1.96 on the left side in the Z table from the Z distribution. So we just compare this value with the sample statistic. If using the formula the computed value comes here, then you all are in the rejection region, and that is why we reject the null hypothesis. And if you lie somewhere here, then we accept or we do not reject the null hypothesis. So this is the way. That part I'll discuss little later, no issue. Now what is the meaning of level of significance? It tells me that if I take some decision on the basis of all these three things, then I'm 95% confident that whatever conclusion I'm going to make, that I'm confident that 95% I'm correct. But there are 5% chances that I can go wrong. There are 5% chances that I can go wrong. Now what is the meaning of this? That also we'll discuss in the further, means either in the next lecture or in the other any particular part, wherever this thing comes there. Now let me take you all to the testing of hypothesis. When we test hypothesis, what actually we do? Simply we know the population mean, we claim, we say something about the population, that is mu. Then we go into the field and we collect the data from the sample, and then we compute some things. Say that you have computed this x bar, and this x bar it lies here. Then what are the next steps? The next steps, all the terminologies which we used in the previous slides, here at the 5% level of significance, with the level of confidence 95%, and with the critical value plus minus 1.96, if I draw all these things, I came to know that my this mu and this x bar, they are far from means each other. If this x bar lies here in this rejection region, then I am 95% confident that the population mean and x bar, they are not same. There is a significant difference. That distance is significant. Fine. So this thing that I can conclude. This is the way that we actually test the hypothesis. Now the other way around, if I compute x bar and x bar comes here, fine. Now x bar previously it was here, now it is not here, it is actually here. Then I can say that there is no significant difference between the mu and this x bar. There is no significant difference. They are almost same. They are near to each other. So it represents mu, no issue. See, here are the important 2-3 statements. If x bar is close to mu, do not reject null hypothesis. Now, what is null hypothesis? What is alternate hypothesis? All these things we'll discuss in the next lecture. Fine. Here only just try to understand that what actually we do here in the hypothesis testing. If x bar is far from the mu, reject the null hypothesis. What does that mean? If it is near from mu, don't reject the null hypothesis, and if it is far from mu, somewhere here, then reject the null hypothesis. How far is significantly far? That we determine using critical value and p-value. So critical value, already we have seen that critical value is nothing but the value that we compute from the table like Z table, T table or chi-square. There are different tables available in the book. But so far this course is concerned, there is really no need to go to the tables. There is really no need to go to the formula. There is really no need to remember this graph also. No need. This graph, this lecture, the objective of this lecture is to just make you familiar with the technical jargons that we use in the hypothesis testing. If you remember that the 5% level of significance is there somewhat, there is a critical value in Z that is plus and minus 1.96, then that's enough for the hypothesis testing. However, let me take you all to the further slide. So to test the hypothesis, there is some procedure that we should follow. The first thing that we should set up a hypothesis, null and alternate, then we should go for the suitable level of significance, then we should choose test statistic, then we should decide the approach to test the hypothesis. There are different approaches, and finally we should go for the comparison and to make the decisions. So all these procedures will try to understand in the next lecture. In the next lecture, I'll go to the meaning of all these things and I'll explain you what actually and how actually we test the hypothesis. So for this lecture is concerned, I just wanted to make you familiar with the few technical jargons or the terminologies which actually we use in the hypothesis testing. Till next lecture, we'll stop here. Thank you for your kind listening. Thank you.